Hello again. Here we are with techniques of integration for Calculus 2 course, and today we're going to talk about improper integrals of type 1. So what are improper integrals of type 1? These are the ones where we would have infinite limits of integration. In other words, our integral from a to b of f of x dx would be the integral from a to infinity of f of x dx. That's an infinite limit of integration. Or we could have an integral from negative infinity to a. So let's first consider, for example, the integral of 1 over x squared from 1 to t. So t is just some random finite number. And if we just go ahead and integrate 1 over x squared, that would be x to the negative 2, and x to the negative 2 integral would integrate to x to the minus 1 over minus 1, which would be minus 1 over x. And if we integrated, or if we did the fundamental theorem of calculus from 1 to t, we would get the minus 1 over t minus minus 1, which is plus 1. So you can see here that no matter what value of t we choose, minus 1 over t plus 1 is going to be less than 1. But if we actually take the limit as t goes to infinity, we're going to get 0 plus 1. So the limiting area under this curve is actually going to be finite, and it's going to be 1. So it's not always the case, even though it might seem to be, that if we have an infinite limit of integration and we went back to our Riemann sums and went back to the limit definition for the area under the curve, you might be thinking that if we divided this infinite limits of integration into finite and then let the number go to infinity, that since we have an infinite region, we would have infinite area. But it turns out that's not the case. So we want to consider how to evaluate improper integrals. Sometimes it will be the case that you will have infinite area, and if you do have infinite area, you will say that the integral from a to infinity, or the integral from negative infinity to a or to b, is going to be positive or negative infinity. And in that case, you would say it's divergent, right? So, but if we converge, or if we actually end up with a limiting factor of a finite number, in other words, our area is no more than a given number, such as the case of 1 over x squared, then we can define our area to be that limiting factor. So here's our first definition. So if the integral from a to t of f of x dx exists for every number t bigger than or equal to a, then we can say that the integral from a to infinity is equal to the limit as t goes to infinity of a to t. So how would we actually apply this? We would first, take its antiderivative, right? And we would know that the f prime of x is equal to little f of x. So we would use our standard techniques of integration to evaluate the integral. And then we would embark on a limit of the f of b minus f of a. So we would say from a to infinity, because that would be our first limits of integration. But we would call this the limit, and we would say let infinity equal t, so that we can say t is going to infinity of f of t minus f of a, right? So going back to a review of Calculus 1, we know that the limit of a constant is a constant, so it really is a matter of evaluating our limit at infinity here, right? The limit as t goes to infinity of f of t equals what? And we do know that the limit as t goes to infinity of f of a is just going to be f of a, because the limit of a constant is a constant. It is at this time that I remind Calculus 2 students to go ahead and review your limits at infinity and how to calculate limits at infinity. Originally, you start by factoring out highest powers of t, or highest powers of the variable, in both the numerator and the denominator. And later on, with applications of the derivative, you can employ L'Hopital's rule if you have a 0 over 0 or an infinity over infinity scenario. Likewise, if we have negative infinity to b, we still have an infinite limit of integration. So in this definition, we would still calculate our antiderivative. We would go from minus infinity to b, and then in order to calculate that, we would say we're going to take the limit as t goes to minus infinity, and we're going to let t here equal that negative infinity. So in this case, we would be saying f of b minus f of t. So again, the f of b is going to end up being a constant, and the limit of a constant is the constant. And then it's a matter of calculating the limit as t goes to negative infinity of f of t. Good. And then in the case with truly huge infinite limits of integration, if we have negative infinity to positive infinity, we want to break up our integral using the algebra of integrals, and knowing that behind the scenes we are taking limit definitions of, taking a finite number of partitions to an infinite number of partitions. But in general, most people use a equal to 0, since our f of b minus f of a would end, or f of t minus f of a, when a is equal to 0, your function is really easy to evaluate. So in general, we kind of split up the real number line and use that proper division of 0 is a good idea. And then, of course, you would return to section A and B, or part A and B, and if, just as a note, if either integral from minus infinity to a of f of x dx, or the integral from a to infinity of f of x dx equals positive or negative infinity, we can conclude that the integral from minus infinity to positive infinity of f of x dx equals positive or negative infinity. In other words, it is divergent. We say that our integral is convergent if the limit actually tends towards a finite number. Okay, so let's take a look at this example here. Determine if the following improper integrals converges or diverges. If the integral is convergent, find the value it converges to. Okay, so divergent if it goes to positive or negative infinity, convergent if it goes to a finite number. Before me in example A, I see an algebraic function multiplied by a transcendental. I'm going to use, and substitution doesn't work, obviously, so I'm going to choose integration by parts. And with by parts, I'm going to let, with our Liate, remember L is logarithms, I is inverse trig, A is algebraic, T is trigonometric, and E is exponential. And this gives me a nice little tool to determine what is U and what is dV in our integration by parts. And since x minus 1 is algebraic and it's closer to the U, I'm going to let U equal x minus 1. And I know that du here is the derivative of x minus 1, which is 1 times dx, right? So I'm just going to say 1 times dx is just dx. And dv, since the exponential e to the minus x is closer to the dv part, then I'm going to let dv equal e to the minus x dx. And with a simple u substitution, e to the u du, we're going to end up with minus e to the minus x. So our integral here from 1 to infinity of x minus 1 e to the minus x dx is going to equal uv minus v du for our integration by parts. And in substituting my values, I get x minus 1. V is minus e to the minus x. I'm just going to put the minus in front, and I'm going to put the minus x here. And then I say minus, and our v is minus e to the minus x. And then our du is dx. cleaning things up, I'm going to distribute that minus, and I get 1 minus x e to the minus x minus minus turns into a plus e to the minus x dx, and I can evaluate the integral there directly or using a standard u substitution of u equal to minus x. So I end up with minus e to the minus x again. I can factor out the e to the minus x, and I end up with 1 minus x minus 1. And that's going to give me, with the 1's canceling, I get minus x, and taking e to the minus x downstairs, I end up with minus x over e to the x. And that is my antiderivative. I am going from 1 to infinity, so I do want to say that that is equal to the limit. If I let my infinity equal t, I'm going to say my limit as t goes to infinity of minus t over e to the t minus minus 1 over e to the 1. And I can use my algebra of integrals here and say that that is the limit as t goes to infinity of minus t over e to the t. Minus minus is a plus. And I get limit as t goes to infinity of 1 over e. And this integral, I am going to infinity over infinity, or minus infinity over infinity. So I'm going to employ L'Hopital's rule. And my L'Hopital's rule is going to give me the limit as t goes to infinity of the derivative over the derivative, and the derivative of the top is minus 1, and the derivative of the bottom is e to the t. And this constant here, I'm still just going to continue with that limit and just calculate over here, and knowing that this is going to minus 1 over e to the infinity, which is infinity, and a constant goes to a constant, and that is going to 0 plus 1 over e, which is 1 over e. This is finite. So conclusion, our integral here is convergent, and it converges to 1 over e. Good. All right, I'm going to skip 1 over b, and I'm going to go to, example b, and I'm going to go to example c here. I see a proper rational expression. I don't see a standard u substitution. I do not see 1 over x squared minus 4 inside my basic table of integrals. So I'm going to try integration by partial fractions. Good. So I first start with 1 over x squared minus 4. It is proper because the degree of the numerator is 0, the degree of the denominator is 2, and since the degree of the numerator is smaller than the denominator, I can go ahead and proceed with integration by partial fractions. I do know that x squared minus 4 is x minus 2 times x plus 2. And my partial fraction decomposition, since they're both linear factors of multiplicity 1, I know that I've got a constant above my linear factor of x minus 2, and I have a constant over my linear factor of x plus 2. Trying to find a and b, I then multiply on both sides of this partial fraction decomposition by the entire denominator, and I end up with 1. And if I distribute, I end up with a times x plus 2 plus b times x minus 2. And we assume this is true for all values of x, for x equal to negative 2, which makes that first term of x plus 2 equal to 0. I get 1 equal to 0 plus b times minus 2 minus 2. That tells me that 1 is equal to minus 4b, or that b is equal to minus 1 over 4. Also, for x equal to 2, which makes 2 minus 2 equal to 0, if I plug that in, I end up with 1 equal to a times 2 plus 0. which implies that 1 is equal to 4a, or that a here is equal to 1/4. So in my partial fraction decomposition, I end up with 1/4 over x minus 2 minus 1/4 over x plus 2. Taking my integral, I end up with the integral of 1 over x squared minus 4 dx is going to give me my integral of 1/4 over x minus 2 minus 1/4 over x plus 2 dx. And I can split up those integrals and use the algebra of integrals, so I can pull my 1/4 on the outside, and I end up with integral of 1/4 dx over x minus 2, take away 1/4 times the integral of dx over x plus 2. Making standard u substitutions for both of those integrals, using the u equal to x minus 2 in the first and using the u of x plus 2 in the second, and that turns it into a du over u, which gives us an ln of u, and back substituting, and we don't have any extra factors, we end up with 1/4 ln of x minus 2, take away 1/4 of ln of x plus 2, absolute value. Good. I do want to note that, remember, we are going to use our limits of integration from -infinity to -3, and I want to make note that infinity minus infinity is an indeterminate quantity, and we might end up with that with our ln of x minus 2, because we do see that the absolute value of -infinity is positive infinity, and we do want to note as x goes to infinity, ln x goes to infinity. So we will end up with an infinity minus infinity in the standard form. But I can use my properties of integrals, and remember your property of integrals of ln of x minus the ln of y is equal to the ln of x divided by y, and knowing our limits, the limit of a composition of functions, of continuous functions over an interval, is going to be the composition of that limit. So we can put the limit on the inside. So I'm just going to make some minor adjustments here and factor out the 1/4 and have ln of x minus 2 minus the ln of x plus 2 from 0 to -infinity, and then I'm going to say that that is equal to the ln of 1/4 times the ln of x minus 2 times x plus 2, and now I'm going to consider my limits, right? If I go and let my -infinity equal t, this is going to be the limit as t goes to -infinity of my f of minus 3 take away f of t from my definition of improper integrals, and that is going to be the limit as t goes to minus infinity of 1/4 ln of -3 minus 2 is minus 5 over -3 plus 2, which is minus 1, but we see that minus 5 over minus 1 is 5, so we don't need the absolute values, and we can say that this is ln of 5. And then we want to say take away 1/4 of ln of t minus 2 over t plus 2. Good. And this is going to, the limit of your constant is going to equal your constant, but and the limit of a difference is the difference of the limits, and so we can say that this is minus, and also the limit of a composition is the composition of the limits, provided that those composition is continuous. And we do have that the ln of absolute value, even if t is going to -infinity, we will have a continuous function of positive values because ln of t is continuous. So we can say that this is minus 1/4 ln, and we can take that limit definition inside of t minus 2 over t plus 2, absolute value. And you can perform a L'Hopital's rule on that because you get infinity over infinity, or you can factor out the highest power, but we do see that that is going to 1, and we know that the ln of 1 is equal to 0. And so we just end up with a value for this integral is going to be 1/4 ln of 5. And so we can conclude that this integral here is convergent. So we can say that this converges to 1/4 ln of 5, or the ln of the 4th root of 5 if you want to use another property of integration. Good. We can do part D if you would like, because this is a negative infinity to positive infinity. And remember, if any one of them is infinity, then you can conclude the entire sum is infinite. But first we see that we're going from minus infinity to positive infinity. So we first want to split this up into two separate improper integrals, and I'm going to use 0 of 1 over x squared plus 4 dx plus the integral from 0 to infinity of 1 over x squared plus 4 dx. Okay. And so I first go ahead and approach the first one, and I see an inverse tangent scenario where I have an x squared plus an a squared, where a is equal to 2. So I see that this is going to be 1 over a inverse tangent of x over a from the basic table. And I'm going to go from minus infinity to 0. And remember, when we have infinite limits of integration, we want to let the infinity equal a t. And we're going to say that this is going to equal the limit as t goes to minus infinity of f of 0 minus f of t. And so we end up with the limit as t goes to minus infinity of, and our 1 over a here is going to be 2. So this is going to be 1 over 2 inverse tangent of 0 over 2. Take away 1 over 2 inverse tangent of t over 2. Okay, so if we recall what inverse tangent is going to send an angle to a trig ratio, and inverse tangent is going to send that trig ratio back to an angle where that angle is between minus pi over 2 and positive pi over 2. And what angle has tangent equal to 0 over 2? So tangent of what value equals 0? And that's going to give us 0. So this one is 0. And we're going to have minus the limit as t goes to minus infinity of 1/2 inverse tangent of t over 2. And if we remember our tangent function looks like this. And this is pi over 2 and minus pi over 2. And so we see here that tangent of 0 is equal to 0, which is why we ended up with 0 here. But inverse tangent is going to input your trig ratio and output your angle. And I see if I'm going to negative infinity inverse tangent, this is going to 1/2 tangent of minus infinity divided by 2, which is 1/2 inverse tangent of negative infinity, because a negative divided by a positive is negative. And if I look over at my tangent graph, this is my minus infinity, and I see that my angle is approaching minus pi over 2. So this is becoming 0 minus minus pi over 2, which is going to give me pi over 2. And I don't want to forget my 1/2, and so I want to put in my 1/2 here. And so I end up with pi over 4 for my very first integral. And by the very same reasoning, because I'm going to end up with the same result for 0 to infinity, the integral from 0 to infinity of 1 over x squared plus 4 dx is going to be 1 over 2 inverse tangent of x over 2 from 0 to infinity. And we're going to get infinity minus, right? This is going to equal the limit as t goes to infinity of 1/2 inverse tangent of t over 2, take away inverse tangent of 0. And we know that the inverse tangent of 0 is 0. And we know that the inverse tangent of infinity is going to be pi over 2, right? Because that's the inverse tangent is going to input the trig ratio infinity and output the angle pi over 2. And this is our angle theta. Good. So we will end up with pi over 4 minus 0, which is pi over 4. So we can conclude that this integral here is going to be pi over 4 plus pi over 4 equal to pi over 2, and our integral is convergent. All right, so that does it for the first type of improper integrals, meaning type 1 is when you have limits of integration that are infinite. I'm going to start a part 2 video, so watch out for that, and that's going to take care of the other type 2 where we have points of discontinuity in our function over the range of our limits of integration. Take care. Have a great